Good morning. Let us start. Before we start for today's class, so a couple of announcements. Like we got some email indicating that problem with the system or online systems which has. Uh, we are working on this one, and within couple of days, I hope that I can able to give you some concrete information. Possibly we can be able to arrange some systems in our software lab, and we will provide you the required login information also, so that you can remotely log into this system and you can work. Now, as we mentioned that on the last class and laboratory also, so since we are targeting for a specific instruction set, so while you are selecting your system, if it is not the institute provided or the department provided system that will provide to you, so if it is the case, then you please make sure that is x86 64-bit system, the same instruction set, because finally the target code will be generated on that, and there is some system dependency regarding this one. Okay, so that is one thing to announce. Another, the assignment one is up, and I hope you are able to see that one and use that one. I uploaded the course information in the laboratory page as well as in the theory page of the Moodle server. Now, initial week, as I mentioned, there was a delay, but after this, what will happen? After the every week's class, and we will upload the required lecture slide. I will try to send an email also to you through that your email address that is provided in ERP. But in case you didn't get it, so please check the module we will upload. Okay. Now with this, let us start today's class. Today in the second module we are starting. So do you able to see my presentation?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, thank you. So in the second module, we are planning to cover lexical analyzer generator, so which is called as the scanner also. And there are two utility programs, Flex and Lex, in laboratory, and in this theory class also. We will prefer Flex over Lex because of several reasons. I will come to that one. And we also plan to cover this module today and tomorrow. So the objective of this module is to understand the lexical analysis and understand the Flex specification. So Flex is a utility program. So regarding this one, I will also mention that when we will have the required laboratory. But if you are too much enthusiastic and wish to do the Flex along with this theory class, then I suggest you to install Flex utility in your Linux system. Usually this utility does not come along with GCC. You need to install this package separately, but it is free. You can able to install that one. If you install, then you can do all the examples we will be covering in your program, in your system, and you can see that what is happening. Okay. And regarding this module 2 and lexical analysis, our third assignment, which is planning to be uh, offered on 2nd of September next month. So this week we do not have any lab class. 19th is Moharram holiday. So second lab class will be on 26th, and after that the third lab class, third assignment will be on this Flex. So this is the brief outline, objective, and will be provided first. Then lexical analysis outline, followed by Flex specification. So in this theory class, we will cover some specifications. We will work with some examples. So my suggestion is that please attend these classes, specifically this Flex and Bison, because mostly it will be discussed in the theory class, and only very few things will be discussed in the laboratory, and then the assignment will be placed. So all those, that's why I used to send email to those backlog students also. So if you have only the laboratory, then also it will be not good idea. I will suggest it's mandatory to attend the theory classes. Otherwise, it is not possible for you to do the laboratory. Okay. So after discussing the Flex specification, the interactive Flex Bison flow. So Bison will come for the parsing process, that will come next. Next week we will start on that, and the start conditions and summary will be covered. When I talk about this lexical analysis algorithm, so you can think of the situation that one source program is given to you. Let us assume a simple C program, and for the simplicity, I am also not interested to include that has include stdio.h. Right from int main, I am starting, and that's why inside the program I am not using any printf or scanf statement. Some variable declarations, assignment of the variable with some integer constant, some arithmetic operations with the integer constants and variables. So simple thing. Now, if this is your source program, and as you understand from the last class introduction, that if from this source program, if I wish to generate a machine level code, or say even simpler one, that assembly code, and in the assembly code we have seen that for addition there will be an instruction like add, for copy there will be instruction like move, for jump there will be JLE or JMP based upon the condition. So those, if I wish to convert the source code, then in several steps I have to go. Okay, the first step of course is to identify that what is the meaning of the characters or sequence of characters that is written in your source program. Say int main, so in between int and main there is a space, after main there is opening and closing parentheses. So what are those? So first I have to segregate that one, or I have to separate them. So that separation is usually done in this lexical analysis stage. In the lexical analysis stage, it looks for some pattern, and if that pattern belongs to some token class, then I call that as a lexeme. I will come to that in more detail. Lexeme. Okay, so lexeme is usually called as the series of characters following a particular pattern, and the pattern belongs to some token class. So the series of the characters that I am considering, that will be part of some regular expression or RE. So RE for every token class. So for every token class, I will have some pattern, the pattern in the form of some regular expression, so that when I will scan or look at the source program, then from there I can identify what is the regular expression, and then I can match actually corresponding to this regular expression what is the pattern and in which token class that belongs. Now when I have RE, then I can convert that regular expression to an non-deterministic finite automata. And when I have some non-deterministic finite automata, I can convert that one to some deterministic finite automata. All those things you have learned in the last semester in the class of formal language and automata theory. Now, when we have DFA, then corresponding to that, some lexical actions can be considered. So, lexical action for every final state of DFA. Okay. So, how I will come with an example. Let us consider this situation. Okay. So, this diagram is familiar to you. Now, this is NFA. This is my start state. Here, arrow indicates that this is my start state. Okay. What I am going to realize is three things: float, for, and A to Z. After that, A to Z 0 to 9 star. So you see that float is a token class I am considering for the time being. The name of the token class I am telling, say FLT. For is another token class, say FOR. So in class of your programming and data structure in C language, you have seen that this float, for are kind of reserved keywords. Okay. Now I have to understand that what kind of reserved keyword it is and whether the reserved keyword is correct or not. So you remember that in C, that instead of say FLOAT, if there is a small typo, say instead of FLOAT, you have written FLOAL, then there will be some compilation error. And you will not able to generate a.out file. So that is basically caught at this stage, at the lexical analysis stage, where you will see that, okay, so this pattern whether is present or not, because this pattern belongs to some token class. Okay, so not this one only, because actually when I say that the error you are getting, say FLOL, and it is telling you that there is an error, then only based upon that one, the lexicon analyzer has no capability to tell that there is a mistake. Because based upon the context, it can be the name of a variable, the identifier name. So context is important. So after this lexicon analysis, it will be sent to the parser, the syntax analysis will take place, and then only you can come up probably with some conclusion. That's why usually what happens that in compilation process, there are two boxes. If I say that this is my lex, the lexical analyzer, and this is my parser, so parser asks to the lexical analyzer, okay, give me the next token, and lexical analyzer send the next token. So identifying or tokenizing is the whole purpose of this lexical analyzer. And in the last slide, what we noted that there exists regular expression for every token class. And since there is a regular expression, I can convert that to NFA, then I can convert that to DFA, and when there is a DFA, then I can attach some lexical action for every final state of DFA. Okay. Now this is my NFA. I am supposed to realize float, for, and name of some identifier ID, which will start with some character from A to Z, all small, that you can see from here, followed by there may or may not be, this is knee closer, you see this star. Okay, so this is knee closer. So 0 or more than 0 number of occurrences of A to Z in small characters and 0 through 9 in digit. Okay. Now if I draw the NFA for these three things, float for an identifier, then after the start state, one path is going, say, F, then going to next state, then L going to next state, O going to next state, A going to next state, T going to next state. Now after this T, there must be some other thing. Other means what? It should not be, say, A to Z or 0 through 9. Now you see that after FLOAT, if there is one more character either from A to Z or one more digit from 0 through 9, then it will not be float reserved keyword. It will be something else which is kind of ID or identifier. So that's why if I have A to Z or 0 through 9 after this T, then it will come to this particular state. But if it is not this A to Z and 0 through 9, as you understand, if there is a white space, if there is some other thing, specifically regarding this other thing, I am talking about the look ahead. Note that transition on the look ahead while all others are consumptions. So using this look ahead information, look ahead means when I am at T position, then my cursor is one step or 2 steps. So usually let us start with the one step ahead, and it can see that one, and after seeing that one, it is predicting, okay, it will be the token class FLT. And here you see double concentric circle indicates that this FLT is the final state. But after T, FLOAT, if you have anything like A to Z or 0 through 9, then it will come to this state. And at this state also, there can be any number of self loops on that. And again, when the look ahead will tell that others, then it will go to ID, another token class. And this is also the final state, as is indicated by these double centric circles. Third one is that for, with F first, O next, R next. Again, similar to FLOAT, if I have others, then I will go to the final state for my token class. If it is in something else, A to Z, 0 through 9, then I will go here, self loop may occur, and because of others, I will go to ID. Right? Now this is my NFA. That's why after the start state, upon realizing F, either I'm going here or here. Now if I convert to DFA, then there will be only one single entry. So start state, after this F, then it will be here. Now only this part is different. The rest of the parts are same with the NFA, because ambiguity was there after the start state. Rest is fine. So once you will have this DFA, then basically you can have list of actions for this pattern. Right? Let us take two examples. So in the first example, we will show the integer and float constants. And in the second example, we will discuss the identifier using the character class. So in this constant, integer and floating point, so here you can see the rule, okay, the production rule. So number derives to digits. This OPT frac is also non-terminal, but the name OPT mostly indicates it is optional, but you know that here this OPT, presence or OPT or absence of OPT doesn't make any sense. Separate meaning is not there. It depends upon what will be the production rule corresponding to this OPT frac and OPT expression. Okay. Now, if I look at other rules, then digit will be 0. This is 5, 1, 5, 2, 5 up to 9. The 5, as you understand, indicates that 1 of 0 through 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 will be picked. But if I go for multi-digit, then I have a separate rule, digits. One S is extra here, that makes it different than this digit. It says digit and digit star. So at least one digit will be there. After that, there may or may not be digits. So if I wish to go for multi-digit, then I can use this. As you understand, since digit star is there, so single digit also you can get from here when you will consider that this part will give you epsilon. Okay. Now this opt frac OPT FRAC, the rule indicates dot digit. So here you please see, I am making a small circle. The small dot is there. That is the decimal point. So you should not ignore or miss that one. So the decimal point after that digit, or this can be epsilon, indicates it can be omitted. Nothing will be there. Now opt expression, the third one in the first rule here, third one. So that expression, in how many ways you can write? So definitely this can be omitted. That's why after the 5 there is one epsilon, and there are two choices. This is one choice altogether, and this is another one. Now this E is for the exponential. After that exponential, so you can give sign to the number, positive, negative, epsilon, followed by digit. So epsilon indicates that, or it gives you the flexibility that when the power exponential onto that, so the power is actually positive, then either I can write plus or I can omit that one. So that rule, whether when say there is plus, what will be the interpretation of that one? When there is no plus, what will be the interpretation of, I mean, whether that will be considered as positive or negative. So the lexical analysis part, do not do that one. It doesn't do that one. It just lay down the regular expression, and based upon the pattern, it classifies into different classes and send it to the parser. Okay. Now here you can see that comparing your common sense of the integer and floating point constants, so few modifications you can do. It is not complete, I agree. So first of all, the number can be negative, so we are not including sign here at the beginning. So here you can include some sign by say writing sign, and again with the sign, either the convention of the rule, you can have that sign say derives to plus or minus or epsilon, you can write. Sometimes it is also marked as, in some convention, sign followed by one question mark. Question mark indicates that it may occur, may not occur. Okay, but do not go to that question mark, that is a separate or different convention. So sign plus minus epsilon, and sign you can have at this position. Then only you can have signed number. Otherwise, this example is not for negative. It is not allowing negative. Also, in the optional fraction part, you see that the rule is digit. And if you follow this, then you will see only single digit is allowed. So if you wish to incorporate multiple digits, you can write S here. Similar to that, in opt expression also, if you wish to write or if you wish to have multiple digits, then you can modify these to digits here. Otherwise, digit will indicate only one digit. Okay, I hope this is clear now. Next, go to the FSM, finite state machine, for integer and floating point constants. Starting from this start point, so here this is my start point, the arrow pointing here. Each circle is having one integer number inside that. That integer number actually indicates the state number. You can consider this is my start state or zeroth state, this is my first state, this is my second, this is third. So as such, there is no meaning for this one. This helps you for a clear understanding or explanation. That's why it is there. Okay. Now, from the starting state, you can see that there are three paths. Of course, you can understand that I will also come to that later. These two may be combined. I will come to that one. This path and this path may be combined. But if not, then there are three paths. 1, 2, and 3. This dot, I am making a red box, is the decimal point. This dot is the decimal point. So it has some meaning, and the transition is based upon this decimal point. Whereas this dot is actually a typo here. So better you remove this from your visual. Now, if I have one integer constant, say 1, 2, 3, then what path to follow? So 1, I will come here, then there is a self loop, any number of digit, okay, 2, 3 I will do, and I will be in the state 1. Okay, that is my 1, 2, 3 state. Now after this 1, 2, 3, I may wish to say that, okay, there is one e to the power something. So if I write after 1, 2, 3 e, then from 1 I will transit to 5. Now you see, this 5 is not a final state, and also it should not be, because I cannot have one integer constant something like this. If I write e, then after that some digits will come. Here the option is either you can transit over epsilon, you do not mention the sign, giving you the flexibility that for positive exponential number I may not have any sign, or you can have sign also, positive or negative, that you can mention here. Then you have one digit, only single digit, say 4 is enough to go to some final state. But if you wish to have more and more digits on that one, that is also fine, but everywhere it will be in the state 7. That is my one final state. Now you see that I mentioned that after this plus or minus or e, after this e actually, there may be one or more than one digit. That's why here I mentioned opt expression, although it is digit, but you can add one more s here to indicate that at least one transition is required, because I cannot leave just writing e plus or e minus or just e. 6 is not a final state, but the number of digit must be at least one here, but maybe any number by this self loop. Okay. Now another option from the start state is that after the digit I will have my number something like, say, 1, 2, 3, decimal point, say 4. this can be one floating point constant. If it is, then from 2 to 4, you see there is a transition over dot. So first digit, you will come to state 2. Any number of self loop can generate the integral part. After this decimal point, you are moving to state 4. So that is your state 4 floating point constant. But there is an opportunity that you can write say 1, 2, 3 dot say 4. After that, again, this final state is a self loop. So 4, 5, 6 you can write as much as you want. Or after that, after E, you will go to state 5, and similar to this one, say plus 4 or say minus 5, whatever you wish, you can write, and you will go to S7. Okay. So in S7, either you will have this kind of format or you will have this kind of format. As of now, what we have discussed. Now the third option is following this path. When the number will be something like say decimal point 1, 2, 3, or after decimal point I have one digit, I will go to state 4, and any number of self loop can give you some number, and this is my S4. Again, after this one, I can definitely write say 1, 2, 3, E, and after E, I can write anything say 7. That is my S7. Okay. Now it is more or less complete. So what you can see, if it is integer constant, then I am at state 1. If it is a floating point, then what are the possibilities? So S7, where the floating point number will be indicating like this, or like this, or like this, or S4, where the floating point constant will be looking like this or this. Clear? Now, when you will have this FSM, then you know the action. Say you are reading the source program, the C program that you again wrote, and when say you are writing a lexical analyzer, then you are reading one after another. So when you are reading after encountering one digit, so you can go to this state or this state, or you can basically combine these two states 1 and 2, and you can have one final state here by combining this. Then you will not need this one, but then another transition may come from here, that if instead of decimal point I wish to go without decimal point, that is, so directly like this, on E I will transit. Okay. Now once you will get an integer, you can go here and then you can see it is an integer constant, or from here. Only when you will reach to some final state, then your realization is complete and you declare that it is part of some regular expression or pattern, and the pattern belongs to some token class. So that is my token generated by this lexical analyzer. Okay. Now if I look at the identifier, similarly it is pretty simple compared to that integer floating point constant, because it says ID, so it produces letter, and letter or digit start. So it must start, if you remember that in C program also we mentioned the identifier must start with some character, and there can be character and digits. So it starts with the letter, and letter means what? A through Z, A to Z. Now you see, first of all, when we are discussing this lexical analysis, so we are discussing the lexical analysis with an aim to design some compiler, or for this right now to generate one scanner or lexical analyzer. This is not the C specific lexical analyzer always, but I am giving you the C specific examples because you are familiar mostly with the C programming language, and in your first year you have done C programming language, right? Now for the C language, it is case sensitive. That's why I can write A to Z, uppercase and lowercase. But if you are considering some language where it is not case sensitive, means it doesn't matter whether it's a capital A or small a, both are with the same meaning, then your rule will be different here. So mentioning one A to Z or A to Z is enough. That is the rule, not for the pattern. But for the pattern, you have to look for both the cases, whether the language is case sensitive or not. Because during the programming, so the programmer can write in capital letter or small letter. Now, whether you will consider the capital letter as a separate one compared to the small letter or not, that is defined in the rule. Okay, but you have to read, or in your rule, you have to keep it open, the possibility of having all A to Z, capital and small. If you do not have that one, then it will not tell, say you wrote only A to Z capital but not small. Then for A to Z small, it will not able to classify that one as one identifier. It will not go to that token class. Okay. Digit is similar to the previous one, 0, 1, 2, etc. 9. Now, for this, I do not have any separate slide for the FSM, because you know this is very simple. So there is only one start state. Of course, start state is only one, and there is a transition for A to Z capital or A to Z small. This transition is going to some final state. So only one single character is enough, because you have used a number of single character variables like I, J. Most of the loop variables, most of you have used as a single character one. So this is the final state it can reach. Or here there can be a self loop. So that includes A to Z capital, A to Z small, and 0 through 9. Anything, any number of times you can keep on looping. Okay. Next, if I consider some of the reserved keywords along with the relational operators. So what will happen? So here in this table, you can see that there are 3 columns. The first column is lexemes, which says that a sequence of the characters following a pattern, and that pattern belongs to some token class. So this is my token class. The token name, I will come to that one. And what will be the attribute value? So that will be here. So that way you can see, so I will definitely explain, but these all are relational operation token class. So it is written as relo. Lexemes are different, which indicates that there are several instances of the relo or relational operators. Okay. So first row here is any WS. WS indicates white space character. It also indicates tab and leading line. Usually it is written like this: T/N. Here, this is extra space indicating that space, white space. If it is that character, either space or tab /T or /N, then there is no token name. It belongs to any token class. Okay. So you have seen that usually that is considered as a standard delimiter. Okay. Now attribute value is also not there for corresponding to that one. In your lexeme, if you find IF, so that is my token class IF. It's a reserved keyword, and attribute name, attribute value is Nothing, because it is only one token name. So since there is one correspondence, so I am not giving any attribute value. Optionally you can give, but without that also it will fine. THEN is my lexeme. So in the source code, when you are doing the scanning or lexical analysis, you are reading THEN. After reading that one, you flag that its token name or token class is then, okay, and attribute value is again null, or it is not required. ELSC, token name is ELSC, attribute value nothing. Any identifier, any ID, when you will get following the regular expression that we discussed or the FSM that we have drawn, that will go to the token name ID. Now you see that for all the variables that you declare in your program, all will go with the token name ID, right? That includes not only the variable name but name of the function. So those everything will be any ID following that finite state machine, and its token name is ID. And what will be the attribute value? Actually, the name of that variable will be stored to symbol table. ST means symbol table. You remember from the last week's theory class that finally there was one diagram which indicates that this symbol table interacts with all the modules of the compiler, starting from the lexical analysis up to the code generation, code optimization, that level. So corresponding to the occurrence of any identifier, it will be stored in the symbol table, and when it will be stored in the symbol table, then there will be an address, so that pointer or the address is actually the attribute value corresponding to that ID. That way they will be different. Okay, so this ST or this symbol table entry is not only required for any identifier but is also required for any number. So whenever there is a number, say I am writing x equals to 10, this is just an assignment statement. So x, the variable, name of the variable, will be stored in the symbol table. I will get an address that will be my attribute value. 10 also will be stored will be stored in the symbol table, and corresponding to that the pointer is my attribute value. Now when I will generate the code, if I assume that since you are now familiar with the assembly language code, so if I assume that I am generating the assembly language code, then you know that x equals to 10. This is nothing but the move operation. So where because of this 10, the value will be $10. That was the immediate. Okay. So this immediate, based upon the architecture, either it is required to be copied to the accumulator first, and from there it will be moved to X, or directly this $10 can move to X. So that is my copy. That will be done during program execution. At this stage, I am generating, so I am scanning, and after the scanning, the information I am storing, the information means the variable name I am storing to symbol table, the constant, integer or floating point, that is any number I am storing to symbol table, and the pointer I am giving as the attribute value I'll attach with the token. Then this tuple will be passed to the parser. Parser will do the processing. After that, parser will pass it to semantic analysis. It will do the processing. It will go to intermediate code generator, machine independent code optimization, target code generation. So steps will go. Okay. Now for this operations greater than, less than, equals to, not equals to, greater than, equals to, all are nothing but the token class of relational operator. Okay. So whenever we will encounter this one during the scanning process, we will declare that it is going to be the token class relational operator. Now, how do we discriminate between this less than relational operator with the less than equals to? Because both are relational operator. That discrimination will be done by their corresponding attribute value. Less than in short is written as LT. Less than equals to in short is written as LQ, LE. Equals to is written as EQ. Not equals to is written as NE. Greater than is written as GT. Greater than equals to is written as GE. Okay. Now this token representation, if I put into an FSM for only these relational operations or logical operators, then it will be looking like this. So this is my start state, 0. Then if I get less than, then I will move on to this state. Less than equals to, then I will go to the final state. And since this is less than equals to, so return token class is what? Relational operation, and attribute value is what? LE. If I get only less than, and next the look ahead indicates there is no equals to. So this epsilon indicates that there is no equals to, which means that it can be, say, one integer, because sometimes you know that I can write, say, less than 8. There is no space in between less than and 8. So the look ahead operation that I mentioned in that NF example for float, for an identifier. Okay, so that look ahead will say that there is nothing in the category of this equals to sign. So the inference will be return token class relational operation and attribute value less than. Similar to that, if I first encounter this exclamatory, then it will be considered as not equals to, then not equals to, then it will be return relational operator not equals to any. Okay. Now at this stage you see that when I see not, then I am in a state which is not a final state. But you remember that this not may occur also as a logical operator in front of some variable to indicate negation. So that negation operation we are not considering here. So in this particular FSM, if you have, then it will support a subset of, say, statements in your source program where there is only not equals to symbol. Only not is not supported. So this is the subset of your understanding of the C. It is not a complete C. In order to make it complete, so all other features or additional things I have to add. Okay, so that's why I mentioned that although sometimes I am taking the example for the C programming language, but when we are discussing this compiler, then you can think of, say, there is one programming language. I am designing a black box which will translate that programming language to some other language, maybe assembly language or some machine language. Okay. To complete this discussion, FSM, first if I say equals to and next equals to, so double equals to indicates return rel of EQ. If I say only one equals to, then the diagram will not able to tell me anything, this FSM. But if I incorporate that information, then it will be, say, assignment statement. So my token class will be not rel of. If there is only one single equals to, then my token class will be something like, say, assignment or operator, not rel of, relational operator, just operator. Operator equals to or operator assignment. If I have greater than followed by epsilon, then return rel of greater than. If I have greater than followed by equals to, then I will have preload greater than equals to. Okay, so this is the FSM corresponding to the logical operators that we discussed in this table. But definitely there is a scope of incorporating other operations. As you keep on doing that one, definitely this diagram FSM actually will be more and more complicated and more powerful. Complicated in the sense number of nodes, number of edges, and powerful in the sense that lot of support it can provide. Okay. So with this, let us tell you the flow diagram of the Flex program. Definitely you understand by looking or by discussing up to this one that if there is an FSM, right, and you write a C program, since you are familiar with C, that's why I am telling C, but other program also. If you write a program, then that program can have the capability to act as a scanner. So it will take another, say, program as an input. Say quickly, if I show you this one, say if this is the source code, then up to this discussion through which probably you can understand that you can write one program which can act as the scanner or lexical analyzer for this source code. What I need only that when I will say that opening brace, closing brace, I will mention this is a special symbol, this is a special symbol. When I say get int, then I will say that this is a reserved keyword. When I see X, then I will say this is an identifier. I will store it in some symbol table and give the address as the attribute value. When I see that semicolon, I will say this is the punctuator. I will repeat this one. When I see this one, then I will say this is my identifier. And since the entry has already made to the symbol table corresponding to this X, when I will encounter this X, no further action is required in terms of entering that one to the symbol table. Actually, what happens when I try to enter to the symbol table, I look for the existence of that one. If it is, then I copy that pointer information and store that as an attribute value. No need to enter. But if it is not there, then I will enter and copy that way. But my point is that you can have or you can write one program which will take this code as an input source code and then tokenize that one, generate the lexemes and give the output. It is possible. However, we need not have to do that one because we have a very powerful utility. Initially, it was designed as lexical analyzer, but we will be using Flex, which is an advanced version. In probably 1987, Jacobson actually wrote that one. That is the fast lexical analyzer. Flex is actually 2 times faster compared to the Lex and probably 17 times less memory intensive. So there will be a Lex source program which will contain all the regular expressions corresponding to that, what will be the action, and the Lex compiler, the utility program Flex that I mentioned, will be using Flex, but Lex also is there. Using that one, we will generate a transition table and action. I will show you. It will be looking like a C program, but very complicated C program. If you try to write, it will take time. But if you try to write this Lex source program, it is very simple and easy to write. You will generate this transition table and action, then automata or simulator, which will, this is actually my source program, which will scan the source program for the lexeme, and it will classify into different token classes and output that token class along with the lexeme. Okay, so let us stop here for today. We will continue on tomorrow with this one. So if you have any question, please let me know. Okay, no questions. Okay, then fine. So before we conclude today, just remind you who joined late for them that we are working to arrange some system for you in our software lab. Within couple of days, I will inform you regarding that one. Okay, so if you do not have access to any Linux system, which is the requirement for this laboratory, you can definitely use that one. And I sent you two actually Google form. One is required for your group information. I see that